Hi, in this video we'll talk about exponential smoothing. We'll look at the formula in detail and see why it is important for time series and for forecasting. Before we talk about exponential smoothing, let's recall the previous topic, and it was also a forecasting method called moving average prediction. And remember that one of the characteristics of moving average prediction was the fact that previous values all carried the same weight in making forecasts for the future. And there are lots of cases where that's going to be unrealistic because you wouldn't expect it for all previous values to have an equal weight for the future. For example, there are cases we can think of really easily that the most recent data should have more weight in predicting future values than values from long ago. So the nice thing about exponential smoothing is it allows for that different weighting to occur in the formula. So that's really important. This formula was developed in 1956, so it's an older technique, but still has some good use today, and we'll talk about that as we move along here. Okay, first of all, though, let's consider a time series data value, x sub t, and let's write that in this form of mu sub t, some mean at time t, plus e sub t, that's some error term, where this error term, e sub t, has a mean of 0 and a constant variance, sigma squared. Now, the reason that's going to be important is because this mu sub t is really what we're going to be trying to predict, and you'll see that as we move along here and look at the exponential smoothing formula, which we're going to talk about now. So here is this formula. I've said here in parentheses that it's recursive. We're going to get a good look at that as we talk about this. But the formula looks like this. U sub t plus 1. I know we've not talked about u yet, but that's what that's going to be what we're forecasting. U sub t plus 1 equals alpha. Alpha is a smoothing parameter, also called a tuning parameter, times x sub t. X sub t is just the current value of x at the current time point t, plus 1 minus alpha times u sub t. Now you can already get an idea of this recursive nature of the formula because we're trying to predict u sub t plus 1 and we're looking back at u sub t. So that alone tells me that it's recursive. Now more about this u sub t. What is this thing? Well, u sub t is an estimate of mu t. Recall that we had written each time series value x sub t as a mu t plus et. So this ut is an estimate of mu t. Now, one more thing about this, too. Here's why this works out. Because, remember, x sub t is written as mu t plus et, but et has a mean of 0. So we're expecting that to be 0. So if this u sub t can estimate mu sub t, then it's also estimated x sub t, because e sub t is supposedly 0. So that's one thing I wanted to say about that. Now, back to the second point about it. U sub t is an estimate of mu t, and it is based on data up to, but not including, that's important, but not including time t. So it's looking at the past. X sub t is looking at the future, at time point t, right now. But this u sub t is looking at the past. And that is a convenient combination that exponential smoothing takes advantage of. So 4 key points, we've kind of touched on some of them already, and the ones that we haven't are we've motivated the topic to where it's going to be pretty straightforward here. First of all, number 1, u sub t plus 1, that's how the formula started. U sub t plus 1 is a prediction of mu sub t plus 1. That follows completely from the fact that, well, u sub t is an estimate of mu sub t. So I would totally expect that u sub t plus 1 to be a prediction of mu sub t plus 1. So that's not surprising at all. Secondly, another fact about u sub t plus 1. It's a linear combination. Really, that's just a fancy word of saying the sum of this and this. A linear combination of the current value xt, that's this alpha times xt. It's a linear combination of the current value xt and ut. Well, what is ut? Recall that ut is based on past values, because we had said here ut is an estimate of mu t based on data up to, but not including time t. So yes, u sub t plus 1 is a linear combination of the current value xt and this ut, which is based on past values. So as I said, it's a convenient combination, an appropriate combination of the present and the past. U sub t plus 1, third here, obviously depends heavily on the parameter alpha. Alpha ranges from 0 to 1. Changing that from 0 to 1 really shifts this weight. So it's nice and flexible. That's why it's important. The selection of alpha is an important thing. We'll talk about that in just a few minutes. And then the closer alpha is to 1, the more weight is given to the most recent data. And on the flip side, the closer alpha is to 0, the less weight is given to the most recent data. There could be instances where that would be of interest. Okay, so let's now look at this formula in more detail. This formula, where we're going to let t be 1, 2, 3, and so on, you'll see more about how this is a recursive formula, and you'll also see how it gets the name exponential. We'll do that on the next light board. Okay, let's pick up where we left off on the last light board. Remember, we were talking about the recursive general formula for exponential smoothing. And it looked like this at the top here. I've rewritten the formula, and it's u sub t plus 1 equals this alpha xt plus 1 minus alpha times u sub t. And what we want to do now is let t take on some various values. So let's t be 1 and 2 and 3 and 4 and so on, and we'll see a pattern develop. And from that pattern, we'll be able to learn some things from it. First of all, why is it called exponential? And we'll also get to see more about the recursive nature of the formula. First of all, for any recursive formula, you've got to get the thing kicked off somehow. And the way we're going to do that, it's a pretty standard thing to do, is let u1 equal x1. So we've got this u sub t plus 1, and really u sub 1 would mean t is 0. Well, we're not quite sure what t equals 0 means. It really doesn't have any meaning. So it makes sense you've got to do something. And u sub 1 equals x sub 1 is what we do. Well, let's go to u sub 2. U sub 2, now recall that 2 in this form inherently has a t plus 1 in it. So 2 equals t plus 1 from here. That means that t equals 1. So that means everywhere you see a t, replace it with 1. That gives me alpha times x1 plus 1 minus alpha times u1. Then we can copy the alpha x1, replace the u1 with x1. Why? Because of step 1. Remember, it's recursive. We're going to be looking back every single time at the time point before, or at the prediction before of u1. So u1 equals x1. Distribute the x1 through, and you end up with, and collect like terms, and you end up with x1. So it looks a little strange. u1 equals x1. u2 equals x1. Looks like we're going in circles and not getting anywhere, but we're about to get somewhere. Let's let t be 2. That is, we're looking for u sub 3. If you're looking for u sub 3, you are meaning that t equals 2. That will give you alpha x2 plus 1 minus alpha u2. Remember, u2 equals the step before it. And that would give us alpha x2 plus 1 minus alpha times x1, because that's what u2 equals in the step before. This time, don't distribute the x1 through, simply because I want it to look like a pattern. And if we'll leave it in this form, you'll see the pattern more easily. Let's do u sub 4. In u sub 4, you're really calling t 3. So that would mean we have alpha times x3 plus 1 minus alpha times u3, which we defined in the step before this. U sub 3 equals this term. So we have alpha x3 plus 1 minus alpha times u3, which is this term right here. Plug it in, put it in this bracket. And then let's distribute this 1 minus alpha through. And when we do, we end up with this. Alpha x3 plus alpha 1 minus alpha x2 plus 1 minus alpha squared x1. You can see the pattern here, x3, x2, x1. That's one pattern. Another pattern that looks to be beginning to reveal itself is 1 minus alpha to the first, 1 minus alpha to the second. Let's take it down one more time. Let t be 5, and we'll definitely see the pattern become even more clear. If you're looking for u sub 5, you're saying that t equals 4. So we have alpha x4 plus 1 minus alpha times u4. and that will give us alpha 4 plus 1 minus alpha. Plug in the value of u4 from before, the step before, and put it in this big bracket. And then let's multiply through 1 minus alpha. We have alpha x4 plus alpha 1 minus alpha x3 plus alpha 1 minus alpha squared times x2 plus 1 minus alpha cubed times x1, and so on. Again, you see the pattern, x4, x3, x2, x1. You also see the pattern of 1 minus alpha to the first, 1 minus alpha to the second, 1 minus alpha to the third. You can also think of this first term as 1 minus alpha to the 0, since that's just 1. Now, we can certainly see the exponential name in this method we're using right now, because the exponential piece comes from 1 minus alpha going from 0 to 1 to 2 to 3, and that's why it's called exponential. You could do the same for u6, u7 if you would like, but we think we see the pattern at this point, right? And in general, you could write this in summation form. It's not any better. It gets more concise. But you could write this as u sub k equals the summation of j equals 1 to k minus 2 of alpha 1 minus alpha to the j minus 1 times x to the k minus x subscript k minus j. So this piece right here represents this stuff right in here. And then the very last piece of it is the 1 minus alpha k minus 2 x1. That's this term that happens at the back. Always at the very final term is a 1 minus alpha cubed x1. That's what this looks like. Here it was 1 minus alpha squared times x1. Here it was 1 minus alpha times x1. So that's this piece. And that is the formula in summation form. Now, obviously, while this was algebraically pretty reasonable to write out, really it was just algebra distributing terms and keeping the notation straight. That's not difficult. But if you were having to make these forecasts by hand, that's going to be very computationally intensive. We don't want you doing that. That's not a good use of time. So what do we do about it? Well, we let R do it. And the way that we have R do it is it's TSWGE. Here's the syntax for it. EXP for exponential, dot smooth for smoothing, dot WGE. There's the arguments. First of all, the data set X, that's just whatever data set you're using. The alpha equals, that's the alpha that we've been talking about that ranges from 0 to 1. And we'll talk about that in just a second. First of all, let's go to n dot ahead equals. That's just the number of forecasts ahead that you would like it to forecast. So if you want the next 5 forecasts, you would say n dot ahead equals 5. Back to this alpha. We know it ranges from 0 to 1. If you're just analyzing some data set that you've never seen before, I mean, maybe you've done some preliminary exploratory analysis, but you still don't necessarily know what to let alpha be. But the good news there is that our TSWGE will do that for you. It estimates alpha by minimizing the prediction errors, and that's the way that it calculates alpha for you. So that is the discussion on the formula for exponential smoothing. We will have a whiteboard video in just the next video where we actually look at a real data set and use the syntax that I just gave here in order to make some forecasts using exponential smoothing. We'll talk about that next time. Mm-hmm.